a process can be in order to do this using STAD. So here we go. So this is a method of creating a physical model rather than the analytical model within STAD Pro. We're going to use the basic capabilities of the program. There are a number of methods that are available for creating a model. We could use the tools within the program to generate each of the nodes and the beams and the surfaces. But rather than doing that, what we're going to make use of is the fact that we have this coordinated central repository which holds the data for the physical model. This is in an ISM repository, which is the main tool that we're going to use to communicate between both Plaxis and STAD. So you can imagine this has been created using a program like the Pro Structures or Tekla or even Revit. So that data is hosted in the information. It contains both the physical steel and concrete surfaces. All of So that data is hosted in the information. It contains both the physical steel and concrete surfaces. All of this information is already predefined and clearly not something that we want to reproduce or recreate. So we're taking use of this information from that repository. So we could actually filter out different parts of the model if necessary, define which bits we want and which bits we don't. But here it is already defined. We've got all of our surfaces, our beams, our columns, the central core, all of that ready to be converted into the analytical model that we want to perform the analysis on. But what we can see is missing here is the fact that we have no support on our structure. Traditionally, what would be done is creating a solid, rigid support. So we're putting the rigid supports on the base of each of the columns. But as we can see, we've also got a core where there is a surface, a series of surfaces defining this core, where we would want to include some form of strip footing. The way we do this within the physical modeler is introduce a reference line, and the reference line can be used either for defining loads or defining a section in the model where we would want to have a surface supported, which is exactly what we want to do in this position. So at the base of the column here, we want to create a fully restrained support defined at the base of the central core. This is indicated with the slightly different colored icons here. So now we've got supports for all of the bases of all of the columns and the surfaces, so that when the surface is decomposed into finite elements, each of those finite elements that are at the base of the core will be given a support to represent the strip footing underneath that foundation. The model is now ready to apply our loading to it. So the way we're going to create the loading is identify in actual fact, three different parts, three different loading types. The first one is identifying the mass of the structure. If we were going to be performing any dynamics or finite element or dynamics or response spectrum, time history, that sort of analysis method, we would want to introduce, we need to identify the actual mass that is used in the analytical solution. The next thing is we want to put in our primary load cases that define the loading in terms of dead and live loading. So, for example, the first load case we're going to include is a dead load, essentially just accounting for the self-weight for a static analysis. And for that, we will apply the loading as a -1 loading in the vertical direction, the y direction. Second load case will So here we've got 2 floors to the left of the model and 3 on the right. So those 3 we pick from the model. Because it's we can select multiple things at the same time, we're just, say for the surfaces, then we want to apply a load of 1.5 kilonewtons per square meter on that surface, and the loading is automatically distributed to those surfaces and applied, so that when we decompose it into finite elements, each of those elements will be loaded accordingly. Combining them then into a combination load case using a 1.4, 1.6 for the dead and live. Simple case of just creating that combination and defining it in this way. There are different ways in STAAD Pro for accounting for this, using either the traditional superposition method or creating what we call reference loads or repeat loads. We're using the standard method in this case, just to again for the speed and not necessarily what we're focusing on for today's presentation. So the model is created in the few minutes that we've been looking at this. We've now gone from a blank sheet of paper to a full 3D model, decomposed into its STAAD analytical finite elements, and all of those all connected up, tested and ensured that the structure is properly loaded. So we're now in a position where we can define our analysis method using a standard elastic analysis, using the perform analysis method technique. Allows us to define within STAAD how we want to perform this this method of analysis. Very quick, very performant to produce our set of results. And now to see the results, we just go to a different workflow, the workflow that displays all of the different result types, and our results here for the nodes, the beams, and the finite elements allows us to create that. And here we can see the results for the stresses on those each of those finite elements and how they've been distributed for the different load cases that have been applied. Now, this is clearly all based on the structure being fully supported, rigidly supported, and clearly something that we need to consider separately. So we'll do that in the next section.
Thank you, Carlos, for your demonstration. So this is where I will take it from now. So I will now start the Plaxis 3D demonstration, and I will go through the following steps. First, I will import the STAAD structural model that Carlos has just been using. And then from there, I will start creating the soil geometry, defining the foundation and the loading. I will create the mesh, and then finally I will define the different calculation stages. So I will now start running also a small video clip as well. And this is, so we start a new project in Plaxis 3D. And the first thing I will do will be to start activating the ISM by reading or creating a new model from an existing ISM repository. So this requires to start the REST API of Plaxis, which is now up and running, as you see. And I will now select the ISM repository I want the model to be created for. I use the same file as Carlos did. And then I click on run. And what you see happening right now is that all the information contained in the repository will be read in and interpreted. So first, we first need to go to the structural synchronizer. Sorry for that. So that's correspond to the exact same model that Carlos used a few minutes ago. Well, we use exactly the same file. I will start simply selecting all structural elements and click on update. And this will start the reading of the information contained in this file, and then automatically the Plaxis model will be created in the background along with all relevant material properties for beams and plates. So there is still a relatively large number of objects, so it would take a few seconds to complete the creation of the model. But you see, the model is being built up live automatically. So I think this is, okay, the operation is not terminated. We see the finish, and now we do have the model imported, the complete structural model imported in Plaxis, saving quite significant amount of time. So we just save it. So I can now go through the next step, which is from that model, create the solid geometry. So here we are. So we are now going to the soil mode. And then I will just create the solid geometry, first by adding the borehole. So the borehole dialog box now pops up. I will add a few soil layers. Oh, it seems like for that. I don't know what's starting again. I don't know what happened. It seems like my video clip is starting again. I'm really sorry for that. So I was just explaining you, I was just creating a borehole. It will contain the soil information. So in this situation, we will be considering just two layers, one 10 meter each, with the water level at -2 meters. And for the sake of speeding things up, I have already created some material properties for both soil layers. So in that situation, we will have a relatively soft soil. Could be clay or could be loose sand, very loose sand, resting on soft rock material. That will be the second layer, which you could see now. For this presentation, which would be good enough. So you see here the material is considerably stiffer compared to the top one. And what I will do, I will simply drag and drop material to each created soil layers. And that's it. So this represent the creation of the soil geometry. So what I will do now, I'll try to demonstrate the creation of the foundation itself. So this is, well, I think it should be there in a few. There we are. Sorry for that. So I'm going to the structure mode, and I will now start creating the entire foundation system of that particular model. So what I will do first here, you see, I will start selecting all the points here, and I will copy them in order to create an array. And the points I want to create are supposed to be representing the corner points of the pad, meant to. So just entering here, you see, I've just been creating a copy of those points that you see right now. And what I do now, I will select the point I have been creating previously, and I will extrude them in order to create the edges of this pad. Apply. So, and then finally, continue this operation, just select the line which has been previously created, and again, extrude them in order to create surfaces. Just position myself properly so that I can select only the objects I want to be selected this way, and then extrude objects along the y direction over 1 meter. As you see now, I'm creating top surfaces of the pad. So you will see later on the one for the building part here has to be a bit different. So what you will see now, I will start deleting what I've just been creating and start recreating a new pad just for that specific one. So I made a mistake in my selection. I will do it again. So it needs to be selecting properly everything I like to be removed. Here we are. Just delete all of this. So now give me the points. I will adjust the location of those points. Slightly different geometry for this throttle part. So look here how I can also change the location of coordinate of the multiple selection. You don't have to do this independently. You can do them all at once. And I will also do it for the 2 points there. I think I made a small mistake. So it should be minus 0.25. So let's do this again. And then I will now need to create the inner points of the pad. So this could be done by repeating the same operation of creating an array, so which is basically in that situation just a copy, a simple copy. We do it again, the other corner point. And then just need to do it 2 more times. One here. Let me show you the screen properly. So and this one, and then finally last point. So you see, this way I can create the 8 corner points of that slab. And what I will do, try to highlight something I'm not many people know, which is creating surface by clicking on existing points. This feature exists from a very long time, but this is seldomly used for some reason. So I figured out it was maybe interesting to present it this way. So as you could see, we have all the top surfaces now properly created. So what we will do is select the surfaces and just extrude them in the Z direction to create volumes that will represent all the pad. That's it. With minus 0.5, they are 50 centimeter deep. Apply. Now you see we have all the volumes created this way. So now for the consideration of the source-filter interaction, I will need to create interfaces surrounding those volumes. So this will be done in 2 steps. So I just first decompose the volume into surfaces to create all the surfaces surrounding those volumes, and then I select the surfaces this way. And at once, here you see I can create all the interfaces, which in that case are the positive interfaces surrounding those volumes. Okay, so there is a magnification factor being used, which we will reduce here in order that the interfaces appears closer to the volumes that they belong to. Now you can clearly see where those interfaces have been defined between. So this was for the pad. Now I will define the piles. And here I will, for the sake of this presentation, I will use a mix of embedded piles and volume piles, try to demonstrate both of them. So I will first start by defining the embedded piles. So I need to do some cleaning first. Try to copy existing points in order to place them at the top of the piles meant to be created. So I need simply to make a copy of all of them. So of course, the resulting created points are inside the pad, so they are not really visible, but I can start hiding them this way by just hiding the volume. I know you see all the points that I've just created. So they correspond to the top of the piles. And the only thing I will do, which will be quite simple, I will reselect all the previously created points and I will simply extrude them in the Z direction. This will automatically create half of the piles, you see. So of course, I need to remove those ones underneath the core of the building, because here I will be using a different techniques to represent the piles. I will be using volume piles there. So I will do that a bit later. But now, as you could see, I try to properly set the camera so that I can get very easily a proper selection of the top points. And now once this has been done, I just use the extrusion feature and start creating the piles all the way down to the rock. Simple as that. You see, I have created all the piles. So as we talk here, those piles are only lines. So they need to be given the proper feature, which is embedded beam. So which I will do here. I will create embedded beams over all those files, and now I will assign them the proper file characteristics, which has already been created on beforehand, so you see, those are my embedded piles. And you could take a look at the properties. Here you see the properties of the pile corresponding to concrete. We have a cross section, which is a solid square beam with a width of 25 centimeter, and then I have a linear distribution of 20 kilonewton per meter as the shaft friction on that pile. And I just need now to copy them because there is 2 piles under each pad. So these are the first one. I just select them all, and now I make a copy along the -y direction with the proper spacing, which is half a meter here. And that's it. So you see how I can very quickly generate all those piles. This was for the embedded piles. And now, just to finish with model construction, I will start focusing on creating the piles for the center part, where I will be using volume piles. I will explain you how this can be done. I will be using the same principle. So what I do is try to hide a bit, it's a bit of time, try to select this point to create an array, but I believe this might not be proper points, but I will be again using a bunch of copy and array and extrude that will finally create. So the idea here is to first create the center point of all those volume piles. So okay, do it again. Select this point to create an array. I think this one is a good one. 1D custom direction 125 x and y should be minus 0.25. Here we are. So now we see properly. So try not to select that point. I think I will first do a bit of cleaning. Select all those nodes. Okay, and now, try to create an array. So first array, define the first row of piles. We do the array in the y direction. Here we are. So I think we have multiple copies, 6 with okay. So now those are I will now select all those points and copy them for the other wing, just by using the array command one more time. So it should be 3.2 meters apart. Should be okay. Oops, see, I made a small mistake. It's the wrong direction. Let me do this again. So it should be minus 3.2. Sorry for that. And now finally, we need to have this last part here. So I will take this one and create finally a last array. And from this stage, then after, it will go all very quick. I think I have 5 occurrences with a spacing of minus 0.64. So do you see, those correspond to all the piles. Here I need to specify. So what I will do now, I will make, again, a selection of all those points. create an array. The array will be the corner of the volume pile. So I will finally use exactly the same techniques that I used to create the pad, actually. So I create all those nodes. I think I will be hiding those ones, and no, I've chosen to select them one by one. It's a bit of a tedious work. And then choose to create extrude along the X direction, and also to be the Y direction. Okay, do it this way. And now one last extrusion. Select all the lines, select the extrusion tool, and then extrude along the X direction is minus 0.25 or plus 0.25. Yeah. So this now creates some, I would say, the footprint of the volume piles. And the last thing I will do is select all the previously created surfaces, which I will do this way. I'm properly setting my camera. And I think I'm having some difficulties here. I will first maybe hide this one. Okay. Sometimes just better do a and here we go. So selection is completed. Extrude. And that's it. So those are the volumes. I will also now again select them. I need to have again a proper angle, so I will select them and decompose them into surfaces, because if I want to introduce, and now I have all the surfaces, I select the surfaces over which I can create, first decompose into surfaces and create, positive interfaces like this. There's been some question asked to me during my presentation how to generate and obtain from this volume pile structural forces, because those piles are being modeled as volumes. The calculation will only provide as results stresses. So one technique consists of introducing what we call dummy beams, which is what I'm going to demonstrate right now. So along the central line of this volume pile, I will create a beam, the purpose of which is to monitor the evolution of the change of curvature and elongation, axial deformation, without introducing significant additional stiffness. And based on the elongation and the change of curvature I will obtain for this dummy beam, I will be able to calculate directly the normal force and the bending moment by simply using beam theory. So that's why we do it. So we create the lines by extrusion, we create beams on those lines, and then once we have those beams, we create here a dummy beam. See, this is what I'm doing now, live. And here, I will use the exact same characteristic as the volume pile. So I will use a rectangular beam with a width of 25 by 25. However, if you look carefully, the stiffness here is 1,000 times lower than the stiffness of the concrete the parts are supposed to be made of. This will guarantee that the additional stiffness added to the beam will be insignificant compared to the original one. However, in output, I will simply need to look at the results in terms of normal forces and bending moment obtained for these dummy beams and multiply them by 1,000, which is the ratio by which I have divided the stiffness in the first place. And this is the concept of the dummy beam, which I'm using here right now. Finally, to make the model complete, I need to add the load, because this is not something which is being stored yet in the ISM file. So I'm just creating a dead weight load on the plate. And then finally, this brings me to the mesh module. So now I have my geometry of the model which is completed, and I will simply create a mesh. The mesh will be generated. I think it's done quite rapidly for that situation. Here we are. So now we have a mesh, so we can very briefly inspect the mesh. We can take a look. So output is now started. It's starting for us to be able to visualize the mesh. So here the mesh. See, with automatic and proper refinement of the soil around the foundation. Trying to scale things down a bit to limit the amplification of the interfaces. Now we could start hiding, you see here, and you could start to see here the model. You could see everything inside the soil, the piles, the embedded beams, as well as the volume piles. So this is my mesh, and then finally, you could see how we could define the different calculation stages. So initially, there is not much to be done. We will have a K-knot procedure to generate the initial stresses in the soil. The third phase will consist of activating the structural elements. So what we do see right now are the volumes representing the foundation. So I'm first activating all structural elements, the plates, the beam, the embedded beam. And the one last thing I need to do is to change the properties of the soil into concrete at the location where the volume piles and the pad are meant to be introduced. So this could be done here by simply creating a concrete material, which will be linear elastic, non-porous. Try to use a color 25 kilonewton per cubic meter, and then 26 kPa 0.2 Poisson's ratio. That's it. So this corresponds to, and I will assign them. So this is the activation. You see now everything. Oh, I forgot this one. You see there. Good thing of using nice colors. Here we are. So this corresponds to the phase of the activation of the all structural elements. And then last phase, just activation of the load case. So in this situation, for this demonstration, we just have one load cases, but you could add as many load cases as you wish from phase number one. And this is how you could create a complete model from scratch with a structural inside in 25 minutes. And the calculation is now starting. So this is the end of my presentation. I will now hand it over to Carlos for the last part. Carlos, up to you.
Okay, thank you very much, Richard. So, yeah, it's amazing what can be done within that 25-minute period. I've managed to keep an eye on some of the question and answers. So I've pushed some answers out. So I've been able to address a few of them that relate particularly to the STAD questions. Hopefully that will be helpful for those that have raised that question, those questions. So, I mean, from the story so far, we've been able to essentially create a model, a structural model that we used with we used the ISM interoperability and repository as a mechanism for transferring the structural data. Some questions have been raised already about the loading data. So at the moment we are considering just the geometry and the structural stiffness. So there are developments we will talk about later on. But now we've want to take on the information that has come from a Plaxis analysis, and how do we actually make use of that back in STAD? So the Plaxis has accounted for the behavior of the soil and the conditions underground, and from that produce a set of data which gives us information that we can use back in STAD. The primary part being the behavior of that soil under each location can be converted from the behavior, the displacement, into a set of equivalent spring stiffnesses. So those spring stiffnesses are something that we're just going to put into a spreadsheet, and from that spreadsheet, I will pull that directly into my STAD model. We'll then rerun the analysis, just show how to pull that data in, run the analysis, and compare the results, and if we have time. So we just pushed onto the next slide, and here we go. So now we've got a set of results from our Plaxis analysis. How are we going to be able to make use of that? And the way we do that at the moment is by using the information that's come from Plaxis. Here it's been put into a spreadsheet. And so from the spreadsheet, we've got information about displacement forces and an equivalent spring stiffness. And that's exactly the sort of information that is now vital for our analysis. So we want to change our supports from being fully rigid to have spring stiffnesses as defined and calculated through the Plaxis analysis. The way that we do this, first of all, is by considering the fact that the spring stiffness that we want to use on each of our supports needs to be added to the model. We've got a table here of spring stiffnesses. So what I'm going to do is I'm going to take the data from that spreadsheet and just use simple copy and paste to take the data. I'll just organize it into another table within the in the spreadsheet, and just copying it. It's just been organized into columns that correlate with the data that we want in our spreadsheet table here, and use the paste information to put the value to those springs based on the Plaxis analysis. You notice that the supports are still being shown as rigid. So what we need to do is identify again those that are rigid and those which are sprung. And again, I've just put that into a simple table here, just changing the fixed to springs as necessary, the degrees of freedom that we want to consider. And by putting that into the table, copy and paste, once again, the data is imported there, or it's included there, and we can see the indicator for each of the supports has changed from being that solid block into the spring, indicating the directions that has been converted into springs. So now we know that the behavior of the structure is going to reflect the underlying soil conditions that the structure is being designed to sit on. This will obviously impact our results. So here, just refreshing the data, the model has changed. The icons you'll notice have also changed on my analytical model to reflect those changes in the definition of our supports. We've got everything in place, and I just simply need to rerun the analysis and update the results based on that new behavior of the support conditions. And here, by going to the post-processing, I'm now getting my results both for the individual nodes, the behavior of those nodes, how far they've actually deformed, utilizing the spring definitions for each of the primary load cases. And also one of the other things that we could have done as well, haven't done in this instance here, is define the supports to be compression only. Clearly, if we're looking at a structure where part of the model may rotate and the structure pulls out of the ground, we would need to consider the fact that that is a one-way support, and we can have it as compression only. And here, just simply showing the effects, the difference in results resulting from that change in our support conditions. So that gives us a sense as to the methods that is currently available to pull the results directly out of the Plaxis system. As I said, just needs a little bit of organization from pulling the Plaxis results into a spreadsheet. The other thing that we can do with the data is to make use of the displacements, and let's see if I can. Not sure if this is displaying. Okay, yeah. So we can just make use of the actual displacements that have occurred. Although the loading hasn't been taken directly from STAD, we can use the information for the loading that has been used within the Plaxis analysis to determined an actual displacement that's taken place, and from that we can pull the structure and automatically generate a set of forces on the structure due to the displacement that has taken place at the nodes. So we should push this forward. We should hopefully get a very short video that explains the behavior. So here's an opportunity for us to make use of the information from Plaxis, where we have found out the actual displacements that have been resultant of their analysis. The way we're going to do this is by introducing a new load case into the model that will include the actual displacements that have been part of that soil analysis. And we'll put that in as support displacements. For us to do that, we're going to have to revert back to our rigid displacements, our rigid supports, so that they have the fixities that we can prescribe those displacements against. The first stage is to have those defined and then go back to the spreadsheet. So this was the information that we had from the Plaxis analysis, which included the displacements in the 3 axes. Obviously, we need to keep in mind the directions and the coordinates of the coordinate systems that are used between the 2 programs. So formatting it into that correct arrangement into a new sheet in the spreadsheet allows us to copy that data into a table directly in the STAD Pro analysis, and there the information is ported across, and each of the displacements for each of those nodes has been included as a defined load case. Now this is really just an understanding of giving us an opportunity to understand how that deformation has affected the model, and as we went through that Plexus analysis. So the new loading, the new data is being used to reformat the STAD data file, and now that is now being presented back in our analytical workflow, and we can see the new load case being introduced into our list of primary load cases with all of the basic data. Now there is one other modification that we actually need to do at this juncture. STAD supports two methods for accounting for support displacement, either using a displacement method or a load method. When working with a model with finite elements and plate elements, we need to instruct the program to use a displacement method, which means making one small change from the fixed displacement, the fixed support, to an enforced support. That gives it a different method, as I said, the displacement method, which we can use in this instance. So by doing that, we now run our analysis, and for the three primary load cases, the structure will behave as before, but for this new load case, a soil load case, we've now got a prescribed set of displacements, and from that we can go back and investigate from the analysis results the behavior of the structure under those prescribed displacements. So here, for example, looking at the base of that column, we can show that what the displacement was from the Plexus analysis, and from here, by changing to the different load cases that we want to view. Here, for example, we want to view the soil load case. We can see how those affect the beam members in the structure, just increasing the scale here. And obviously, as before, we can go to our plate model, look at the finite elements, and get a displacement of the stresses and forces on our plates. So that really concludes the part that I wanted to show for you today from the STAD perspective, basically taking the information from a Plexus analysis, or taking the model from STAD to Plexus, using that in order to determine the behavior of the supports, and refining the structural analysis based on the analysis results from Plexus. We clearly have areas where we'd like to extend the behavior of the program and behavior of the interop. There are a number of good ideas that have been forwarded, and even today in the discussions, I've seen some good ideas and some suggestions for continuing that development together is going to be a benefit not just to the structural engineer or the soil mechanical engineer, but to the whole project and the delivery that the projects are working on. I'm struggling a little bit now because I think I've essentially got to the end of my slides. Unfortunately, my view has just stopped working, so I'm going to have to hand it over to Audra. I think it's about now to hand over to the poll question and some questions for you guys on today's presentation. Thank you.